Hi, everyone, and thanks for joining me for this talk. I'm Giovanni Alberto. I'm the CTO at Xane, and today I'm going to be giving you an introduction to Xane Pulsar. I'm going to tell you what it is, and then I'm going to also discuss briefly what Xane is doing together with the Yocto Project to advance open source embedded security. So let's start off with an overview of what Pulsar is, what it does. And then the plan is to go and dive deeper into some of the fundamental building blocks of Xane Pulsar. So first and foremost, Pulsar is an open source threat detection agent for Linux system powered by eBPF. I will explain more about what this means in a second, so please bear with me. Even though it can run pretty much on every operating system and any Linux distribution, Pulsar is designed from scratch for embedded devices. So it has a focus on really performance and easy integration on any underlying platform. It was designed for this purpose from the very scratch. It is written entirely in Rust, which, as most of you may know, is a modern programming language, provides lots of benefits, including memory safety and great performance. And again, as I said, it's open source. You can find it on our GitHub, xane.io/Pulsar. So how does Pulsar really work in a nutshell? Essentially, Pulsar uses eBPF to collect runtime information from the Linux kernel. Now, what this information is, it can vary a lot, but essentially, it might be any information related to process activity or any activity on the file system stack, for example, on the networking stack, anything that's happening inside the kernel, we can use eBPF to trace that. Then, once we have the raw low-level information, Pulsar packages this information into what are called events, which are essentially a high-level abstraction of that raw information. And events are a fundamental concept in Pulsar because they are essentially the interface between the developers that are using Pulsar and the kernel data. So as we will see later on, events are really the building block which we use to write security policies and thus generate threats on the device when some potentially malicious activity happens. And finally, of course, as I was saying, when we have some particular conditions that are user-defined, which we call security policies, when these security policies are triggered or are met by any particular Pulsar event, Pulsar generates a threat event. So essentially, this is the whole flow. We collect information from the Linux kernel, transform it into event, apply security policies, user-defined security policies on top of those events. If the policies are met, we get a threat event or an alert. But what is eBPF and why are we using eBPF? Some of you may be familiar with it. I thought it would be worth just briefly giving an introduction to this topic. Essentially, eBPF, or extended Barclay packet filtering, is a relatively modern technology exposed by the Linux kernel that enables us to run programs inside the Linux kernel in sandboxed virtual machines. Now, what this means in practice is that with eBPF, we can write user space applications that can tap into all the richness and granularity of kernel space data, with some key benefits like near native performance, full safety over kernel modules, and great portability across different kernels. Now, essentially, these advantages are so important that eBPF today is unlocking a new generation of applications in many fields, most importantly in the networking, tracing, and security fields. So now that we have a high-level understanding of what Pulsar does and about the key technologies that it leverages behind the hood, we can take a closer look at some of its fundamental building blocks, and we can also see some capabilities of the tool. So first and foremost, I would say that Pulsar was designed from scratch with a modular architecture in mind. So in Pulsar, every feature is implemented as a module, and each module is entirely independent on all other modules. So you can think of a module as the bridge between the user space application, the user space daemon, and all the activity that is happening in the kernel. So we can see here 3 examples, probably the most important modules in Pulsar: the file system module, the networking module, and the process monitoring module. But in general, modules can be really both producers and consumers of events. So they allow developers a lot of flexibility. So you can ingest and digest any kind of event or any kind of information on the shared event bus. So it's possible to enrich, in theory and in practice as well, it's possible to enrich kernel level data with any additional information. So this allows for great flexibility of and richness of events. As I was saying, the 3 most important events are most important modules in here. The file system module is responsible for tracing all the activity that is happening on the file system stack, so the I/O activity on the disk. The network monitor module is responsible for all the activity happening on the network stack. And the process monitor module looks for, essentially keeps track of all process-related activity, such as fork, exec. I will show you in a second what kind of stuff it can do. Why this modular architecture is very important? For a variety of reasons. It has several benefits. The first benefit is it is easy to extend. So we can always write new features as modules, and these new modules won't impact existing modules or any other part of the application in any way. So if we want to trace something else, or if we want to add any new events, there's no need to modify any of the existing architecture. Just create a new module and have it talk to the event bus. The second advantage is that the whole application is resilient in the case of a single module failure. Again, if there is any problem with one module, that doesn't impact at all other modules because they are entirely independent. So the whole flow is unchanged. And finally, as I said, modules are entirely independent, which means they can be started, stopped, configured independently of each other. So this allows for a lot of flexibility, especially in very constrained environment, because it allows developers to decide, okay, maybe I don't need to trace activity on the networking stack. I only wanna look at the file system stack. And I can do just that. I can stop all other modules, look at the file system, and everything will work the same from my use case perspective, but I will save a lot of overhead and computational cost, which is critical in the context of embedded devices. So, as we've seen, really the whole purpose of Pulsar modules is that of generating events in the end. What are events really? I was mentioning this earlier. Events are high-level abstraction of process behavior data from the kernel point of view. So they provide, what does this really mean? They provide a very useful interface for developers because they abstract away lots of raw kernel information. One example would be syscalls. So I can have more stable interfaces when I write my rules by tapping into events, which have a predefined schema that is rather stable, rather than having to write rules based on raw kernel information. What is the flow for events? Once they're produced by the modules, usually they're sent on the event bus, and there they await essentially further processing by the rules engine, which we'll see in a bit. Here are some examples of what Pulsar events look like. Again, they're divided by module in here. So you can see some network events. For example, we have bind, listen, connect, accept, and many more. For example, we have an accept event is generated when a process accepts a connection from a given source, of course. And we have another example of a file created event, for example, that is triggered on the creation of a new file, or a file opened event when any file is being opened by some process. Then we have process related events such as fork, which is generated when a parent process forks and creates a new child process that creates a fork event for Pulsar. Of course, as I was saying, these are really independent of the main application, which is really cool. And it's always possible to write new events, new modules, and expand this ecosystem. So this is what we're doing essentially, and what the community behind Pulsar is doing. The final bit that we need to talk about in order to understand how Pulsar works is the rules engine. So the rules engine essentially inspects all the events and matches them against a set of rules or security policies. Now, security policies they have a very simple structure. As you can see, they are entirely defined by 3 fields. They have a name that identifies the rule, and can be really anything you like. It just helps you identify it. Then they have a type, which is really the event type, and identifies the type of event that we are targeting with the rule. And finally, they have a condition, which is actually the logic that we want to check for in that rule. So here, for example, we have a very simple rule. It's called read sensitive file from untrusted process. What it does, in a nutshell, is it checks every file opened event for the following condition. That is, if the process generating the event is different from SSHD, and the file that is opening, so the file name in the payload, and we're talking about file opened, so the file that is opening is the etc shadow file, then immediately raise a threat event. It's a very, very simple example of how Pulsar works. Of course, this is a very flexible structure, just plain text YAML file that you can write as many rules as you want. But of course, there is a set of default rules. It's available on the open source repo. So that acts as a baseline for developers to get started and eventually customize or expand depending on their specific use case. So another example, a bit more realistic, maybe about some rules in Pulsar would be about the CVE 2021-4034, which is a high severity vulnerability found in PKExec, and it allows essentially authenticated users to perform a privilege escalation attack. Now, I don't want to go too much into the details of this CVE, but essentially comes from the fact that PKExec, which is part of Polkit, doesn't check for empty argument arrays, and assumes there will always be some arguments, and this creates problems for the way the process handles memory, and this vulnerability allows essentially an unprivileged local attacker to escalate, so bypassing any authentication and any policy. So what we do is, in Pulsar, for example, we can look for exec events, and then we can look at the all exec events for the PKExec process, and check that the argument counter is different from 0, because if there is 0, then we might be exposing ourselves to the vulnerability. And below, we have an example of what the detection looks like in Pulsar. So as you can see, we're starting our modules, and as soon as we try and exploit it, we have a threat event being generated by Pulsar. A few words on the technical requirements. So as I was saying, Pulsar is designed for embedded devices, but provided there are some key requirements, it can run pretty much on any Linux distribution. The main requirements, I would say, we need a relatively modern kernel version, higher recall than 5.5 to ensure BPF support and BTF support is guaranteed. And in fact, we need both BPF and BTF enabled. And then we support pretty much all architectures, most widely used architectures, x86, Arch, RISC-V. In terms of compute requirements, usually we see an overhead from 1 to 4%, but that of course depends a lot on the actual use case, on the host machine details, of course. In terms of RAM, you're usually talking about something less than 80 megabytes. And in terms of storage, the whole application comes in at about 11 megabytes of disk space. Okay. This is a quick view of what the roadmap for next year looks like for Pulsar. So right now we are working on supporting containers. Actually, that's already pretty much being accomplished. It's already on the main branch. There will soon be a new release to officialize this. Something interesting we're doing is rewriting the eBPF probes in Rust. So I mentioned earlier, Pulsar is written entirely in Rust. I lied a little bit because the actual eBPF probes are still written in C, but it's something we're working on. We're migrating towards Rust also for the probes. And so we can hopefully drop some dependencies coming from C programming language. And then we have something that we're always working on, such as improved events. As I was saying, we're always working on adding new events or improving existing ones with more information and increased granularity. And one cool thing we're working on is adding context to events. So right now, as you've seen, events are kind of one shot in time. So it's like an atomic operation from the Linux kernel. That's an event for us. We're working on adding context to events. So each event will also carry some traces from the past. And that will allow us to write a lot more interesting rules for some more sophisticated attack patterns. And finally, we're working on a eBPF inline response. It's a bit involved and a rather complex thing to do, but essentially what we want to do is we want to also add response in the kernel space. So right now, as I was saying, you have essentially when any condition from any security policy is met, we are triggering a threat event. What we want to do is we want to be able to respond to that threat event directly in the kernel. So without having to wait for the events to go from the kernel space to the user space and then deciding what to do. We can do it directly in the kernel. It's really cool. And that's something we're working on, but it will take a while. So we can expect to be able to do that by the end of next year. That's a very quick introduction of what Pulsar is, what it does. Now, I also want to talk about how it relates to the Yocto project, of course. And essentially, you can find the meta-hexane layer on our GitHub, and it's the layer that contains both Pulsar and the kernel fragment required to add it to an image. Again, it's on our GitHub, and it's called meta-hexane. It has been tested with Yocto Dampfel, Kirkstone, Langdale, Mikkeldor, and Nanbuild. And it comes with a few system dependencies, mostly CLang and LLVM strip, and some Yocto dependencies, mainly meta open embedded and meta Rust bin. You might be wondering why we're using meta Rust bin. For a few reasons, we chose to use meta Rust bin instead of the official meta Rust because it reduces build time. It allows for much smaller recipe complexity. It avoids the use of third-party tools such as Cargo Bitbake, allows us to use newer version of the compiler, also in older Yocto versions. It just works out of the box. Again, supports older. Now it's possible to use also meta Rust, but in the past, this was just not possible to have meta-hexane on without meta Rust bin. So, a few plans for the future. So again, as I was saying, as our integration, our meta layer works on MetaRust bin, we still plan to switch to the official Yocto Rust ecosystem, which is actually something we're doing right now, switching to MetaRust and Cargo Bitbake. But over the long term, and it's also part of our commitment to the Yocto project, we plan to also work on improving the Yocto Rust ecosystem. There are a few things we would like to see, such as support for multiple versions or support for more up-to-date versions of the Rust compiler, support to use, possibility to use precompiled versions to reduce build times, being able to use Cargo extensively instead of having to use Cargo Bitbake, and in general, just fully harnessing the potential of Cargo. And finally, a few words about how this relates to the Cyber Resilience Act. Many of you may be familiar with this. The Cyber Resilience Act is an upcoming EU regulation that essentially it requires product manufacturers to take some strong security measures into account throughout most phases, if not all phases, of the product life cycle. And essentially boils down to for manufacturers to know that when they put a product on the market, they know that product is secure. So we're talking about security posture assessment. The CRA also requires manufacturers to have threat detection mechanisms and processes in place, and to be able to communicate possible incidents in a timely and effective way to authorities. So this is not, it's actually under discussion right now. It will have a big impact on the embedded market as a whole. And together with the Yocto project, Xane is working to provide more tools and more possibilities for developers to comply easily with the CRA. MetaXane is the very first step towards this path, but there sure will be many more solutions, entirely open source for the community, that we're going to be able to release over the coming months. And also we are about to release a white paper, a joint white paper with the Yocto project, I think sometime next week or anytime soon anyways. And that is exactly a guide for the embedded developer about the CRA. So definitely worth checking that out.